Good morning, guys. So, welcome back to the second lecture on dielectric materials. So, in the last lecture, we saw the mechanism of polarization. How, for example, we started with a symmetric electronic cloud around the nucleus, and in the presence of electric field, how the electron cloud gets distorted, and that's how we get the electronic polarization in the teeny tiny atom inside the dielectric material. Uh, we also define, let's say, in the parallel plate capacitor, Q is directly proportional to V, the charge is proportional to the voltage, and the proportionality constant is called the capacitance. Okay, this is denoted by C. So this C we calculated, it turns out that it depends on the geometrical factor as well of the plates A and D, area of the plate and the distance between the plate. And we also define something called dielectric permittivity, denoted as epsilon. Apart from that, we define something called dielectric constant as K, or relative dielectric permittivity as epsilon r, right? Which is the ratio of C divided by C0, or this epsilon divided by epsilon 0. So 0 here or here denotes the vacuum. I mean, when there is vacuum in between the parallel plate capacitor. We also define something called volume efficiency. All right. So today I'm going to start with the dielectric polarization. So what do I mean by dielectric polarization? It's actually dielectric polarization. It's just the magnitude of the bound charge density. So remember, we defined two kind of charges, sigma s, which was the surface charge density, and then I said in the presence of a dielectric material we have bound charge density, sigma b. So the free charge actually gets less effective. So ultimately it's sigma s minus sigma b, the effective free charge. Okay, so the dielectric polarization, it's denoted as P, capital P. So it's the magnitude of the bound charge density. So there's going to be 2-3 definition of this dielectric polarization. So let's say the first one is magnitude of sigma b. Okay, so you remember how the stress and strain are correlated, right? Because let's say when you apply stress, which is a cause, it gives rise to strain, which is an effect. So similarly, the and stress and strain, they are related by something called Young's modulus. I hope you remember this thing. So in the similar fashion, so it's the applied electric field and the polarization, they are related. So the electric field is the cause, and the polarization is the the polarization P is the effect, and they are related by dielectric constant. Constant, which we are denoting as K or epsilon r, right? Okay. So this is the, let's say, just to give you an understanding of cause and effect. Now, if we need to define, I'm giving you another definition, as I said. So one was this magnitude of sigma b. So the another definition is, so for example, let's say we have n number of small, we have n number of small dipoles. Which have, let's say, two charges. So let's, each dipole would be something like this, right? So let's say I'm denoting it by QD. Minus QD, this charge is plus QD. And the distance between it is x. So the dipole moment of each of this dipole would be QD times x. This represents the polarization of individual atom. Polarization of individual one. But the dielectric polarization P, it's the total dipole moment per unit volume. Of the material. Which means that if I say QD is the dipole moment of each atom, so the average of the dipole moment will be, let's say I denote it like this, the average of dipole moment would be denoted like something like this, QDX. So RP, which is from the first definition, is equal to the bound surface charge density, sigma B, is equal to n times, because the number of small dipoles are n, multiplied by this average dipole moment, QDX. Okay, so this is the second definition of the of P, dielectric polarization. We can also denote this average dipole moment, this thing, as mu. So then we can write P is equal to n mu. Mu is the dipole moment basically. And this mu can be written in terms of, mu is average dipole moment. Okay, let me just write it down. It should be average dipole moment. So this mu can be written down in terms of the polarizability, alpha. So I'm defining another quantity. Let's define alpha as something called polarizability. So our mu, it's equal to alpha times E, where E is the local electric field. Okay, so if I ask you what will be the unit of this alpha, so unit of alpha, SI unit. So the unit of mu, mu is the dipole moment, which will come from this QD. It will be Coulomb times distance, meter. This denotes the dimension of mu. Dimension of E, let me write it like this, is volt per meter, right? Electric field. So by this relation now, mu is equal to alpha E, you can calculate the dimension of alpha. So it will turn out to be Coulomb volt inverse, or Farad meter squared. But in general, we represent it as, let's say, something called alpha volume, which will be equal to 10 to the power 6 divided by 4 pi epsilon naught times the alpha, and this unit of this alpha volume would be either, let's say, centimeter cube or angstrom cube. This is the more used expression. This is called volume polarizability. Volume in the sense that it's distance cube. All right, so now we will put down the value of this mu into this equation. Let me call this equation at equation number 1. This is equation number 2. So from 1 and 2, our P will from 1 and 2. So P is equal to N times alpha times E. Okay, and this is our equation number 3. Alright, so this is one way of writing P, the dielectric polarization. I will calculate this P using some other quantity which I'm going to define, and then we'll equate equation number 3 to that. So the other quantity that I would like to define is called dielectric flux density, and it's denoted as D. So this dielectric flux density D, it basically has two contributions. So let me first write it down, P plus epsilon naught E. So the first contribution, this comes from the bound charge, right? Because P is just the magnitude of the bound charge. And the second contribution comes from the free charge. See, because this epsilon naught is telling you we are talking about the free charge. Free charge density. So this is the definition of this D. It has two sources of D. So one is the bound charge plus the second source is the free charge density. I can write it down. I can write down this D is equal to epsilon times E. Okay, the I can say that this D you also know from electrodynamics. It's called the displacement. So let's say it's dielectric displacement. Now, if I use these two, equation number 4 and equation number 5, our P will equal to epsilon minus epsilon naught times E. So this is, let's say, our equation number 5. So we have P is equal to NL phi from equation 3, and from equation 3 and 5, if I'll equate them, so I can say that the form, once I'll equate them, I can write down the form of alpha. So this is equal to epsilon minus epsilon naught divided by n. Okay, so we can rewrite this equation, so which will be something like epsilon r is equal to epsilon divided by epsilon naught is equal to 1 plus n alpha divided by epsilon naught. So epsilon r is basically relative permittivity. Okay, so this is our final equation. And what is the importance of this equation? Equation number 6. So importance of equation 6 is that this connects the dielectric constant. See, epsilon r or k I can say, right? Both are same. So it connects the dielectric constant of the material to the polarizability of the atom. This alpha, and the concentration of atom, which is m. Okay, so the dependence emerges directly here, which was hidden till now. So apart from the two quantities, the dielectric polarization and the alpha, the polarizability, I'll introduce hopefully the last quantity, which is called the dielectric susceptibility. And it's denoted as chi e. Okay, so this chi e, it's when we write down P is equal to chi e times epsilon naught times e. So this is the thing, the chi e, which connects the polarization and the electric field, the cause. So this electric field was the cause and P was the effect, right? In the beginning I told you, like the stress and strain, the once you have a cause, you'll have its effect as well, in simple language. So similarly, if you have electric field, you have polarization as well. So they are connected via this chi e epsilon naught. You might wonder what this E is. So E is basically for the electric susceptibility, the E, because later in the second half of the lectures, you will study something called magnetic material, and there the magnetic susceptibility, which will be chi m. This will be magnetic susceptibility. I'm not writing the full thing. So just to distinguish those two things, it's E and M for that. So now we can compare the P is equal to chi E epsilon naught E equation and the equation that I think it was, let me just, yeah, the equation, you remember we wrote P is equal to epsilon minus epsilon naught times E. So which was equation number 5. So this was equation number 5. So from 5 and let me call it 7. So this is equation number 5. So from 5 and 7, I can write down chi E is equal to k minus 1, or which is same as epsilon r minus 1. Right? So this is a really nice expression because it tells us whenever k is equal to 1, chi E is equal to 0. What's the example? Let's say for vacuum. So this k is equal to 1 for vacuum. This implies that the susceptibility chi E is equal to 0. This is also this is expected, right? Why? Because there are no atoms or molecules in vacuum. So that's why the susceptibility has to be 0. Okay, let me tell you what dielectric susceptibility physically describes. It describes how much susceptible or polarizable a material is. So if there is no material, so there is no dielectric susceptibility. So let me just write it down. So chi E describes how much the material, how much susceptible or polarizable the material is. Okay, so this is what chi E describes. Okay, so I can say this expression as equation number 8. This is also a nice expression. But if, let's say, now we can say that the if the atoms are more polarizable, I mean atoms, ion or molecule in the material, this tells us that the chi E would be higher. So for more polarizable atoms, chi E would be higher compared to the vacuum case, of course, where it's 0. Okay, so in this topic till now we have introduced let's say most importantly 3 quantities. The first one is the dielectric polarization itself, which is the P. The second one is the polarizability, alpha, and we said that the most general use generally we use something called alpha volume, which just depends on alpha and has the unit of kind of volume. Oh, okay. I think there's a mistake here in the dimension. It should be times meter squared also, right? In the alpha, because mu has cm and E has v by m. Yeah, okay. Okay, so just to clarify, it's, yeah, that's why it's farad meter squared. So here it's correct. Here it has to be meter squared. All right, so anyways, so it was alpha volume, and at the last, while introducing dielectric flux density, we also introduced something called the susceptibility, chi E. So these are the 3 things that we introduced, P, alpha and chi E in this section. Okay, so these were introduced. All right, so the next thing that we are going to see, the next topic is the local electric field. So when we examine the effect of, let's say, external applied electric field E on a dielectric material, so we need to consider the electric field which exists inside the polarized materials, right? Meaning that whenever in a solid or liquid, so when we put it in the presence of external electric field, the actual field will be different than the applied field. Why? Because there is also because of the polarization of the atoms, molecules or ion inside. So this internal electric field, this is known as the local electric field. So I can just write it down so that you'll have a proper definition. So for a solid or a liquid, so just bracket L, right, in the presence of electric field. In the presence of E, the actual field experienced by the atoms or ions or molecules, whatever you are considering in the dielectric material, is different from the E. And E, when I say, that means the external applied field, right? The external field. So this is called as internal or local electric field. Okay, and we will denote it using. So in general, if the polar nature of the material is large, then the strength of the dipole would be large, right? So that's why the local electric field will be large. So I can just say that more polar the material is, this implies that larger the local electric field. Okay, so and also actually the magnitude of this electric field which will be experienced by the atom or ion, it also depends on the arrangement of the dielectric dipole. So actually when I'll talk about the different polarization mechanism, that time you will see that how the orientation or the arrangement of the dipole contributes towards the polarization. All right, so for so this formula, the formula that I'm going to write now, I'm not deriving it, but in your assignment you'll be given a problem just to see how this thing comes in. So for a cubic structured isotropic material, or you can one can consider an amorphous material, the form of E local is equal to E, the external electric field, plus it also depends on the polarization. Okay, so this formula we will derive it in the assignment. So this formula is actually called the local field approximation. Okay, so, but we also know that the polarization is equal to n times alpha times E, and there I told you that it's E local, right? We just denoted it that time just using E because I didn't introduce the concept of E local, but now we know what is E local is, and I can calculate from this equation an alpha is equal to P divided by E local, and we can put down the form of E local from above equation, so it will be P divided by E plus P divided by 3 epsilon naught. Okay, but we also know the form of P in terms of the external electric field. It's P is equal to epsilon minus epsilon naught times the applied electric field. So let's say, okay, have I given any equation till 8? I have gone. So let's say this is my equation number 9, this is 10, and this one is 11. So using from equation 10 and 11, you can write down an alpha is equal to epsilon minus epsilon naught times E divided by E minus epsilon naught times E 3 epsilon. So you can actually eliminate E from here, and we can rewrite epsilon divided by epsilon naught as epsilon r, which is the dielectric constant. Or relative permittivity. That's why this R, right? Okay, so then this formula, the final formula becomes epsilon r minus 1 divided by epsilon r plus 2 is equal to 1 divided by 3 epsilon naught and alpha. This is really famous expression, this final expression. I'll call it equation number 11. So equation number 12. So equation 12, this is known as Clausius-Mosotty equation. I'll tell you why it's really famous. This is Clausius-Mosotty equation. So this equation is popular because it describes the relationship between a dielectric constant, which is this alpha r, okay, and just to tell you, alpha r is a macroscopic quantity, okay. It depends on it changes from material to material, and this quantity, it depends on a microscopic quantity. What is it? The microscopic properties, which is alpha and n. Alpha is the polarizability of the individual atom, right? And n is the concentration, I mean number of atoms per unit volume. So this is a relation where you have direct dependence. You calculate the direct dependence on a macroscopic property via a microscopic property. So I can just write it. So these are microscopic quantities, and this one is macroscopic. All right, okay. And also, as I said, that this equation is the Clausius-Massotti equation. It cannot be used for a polar material with permanent dipoles, because see, in deriving we are not using explicitly there is an extra E factor coming from a permanent dipole. For example, what are permanent dipole? For example, H2O, the water molecule, which has a permanent dipole moment. So this equation is not valid for, I'll just write it down, not valid for polar material with permanent dipole moment. So this is an star. Okay, so in this equation number 12, actually we can correlate this concentration N to the Avogadro number. So the N is the concentration of dipole of dipoles, which means that the number of molecule per unit volume. Okay, so I can write it down, N, if let's say we consider each molecule or atom becomes a dipole, then N is related to the N Avogadro. So N would become N Avogadro. I'll just write it AV times rho divided by M. And what is rho and M? Rho is the density, which will be in, let's say, kg per meter cube. And M is the molecular weight. Which will be in kg per mole. And just to remind you guys, so the unit of N Avogadro is generally, I mean, you know, I hope you remember the value, 6.023 into 10 to the power 23, 023 into 10 to the power 23, and it's molecules per mole. So that's why when you will, I mean, if you will see dimensionally also, so that's how the right hand side becomes just the number of molecules divided by volume, because kg cancels, mole cancels. Okay, all right, so then the formula number 12, which we wrote, equation 12, the Clausius-Massotti equation, it becomes epsilon r minus 1 divided by epsilon r plus 2 times m divided by rho equal to N Avogadro times alpha divided by 3 epsilon naught. Okay. Alright, so this is one of the equation in terms of N Avogadro. Also, sometimes we can call this the right hand side N Avogadro. just write it down, its name, it's N Avogadro is equal to N Avogadro times alpha divided by 3 epsilon. We call it molecular polarization, which is denoted by PM. So it's, let's say, molar polarization. And so this is about the Clausius-Mozart equation. Also, I didn't tell you what are the different contribution to the alpha. Alpha is the polarization, right? So in the next topic, actually, we'll see all the 5 mechanism for polarization. But in general, this, for the sake of the Clausius-Mozart equation to be valid, the alpha is generally alpha E. Just take my words now, you will understand what is alpha E and alpha ionic in a second. All right, so this is the electronic part and this is the ionic part of the polarizability. All right, okay, so we are more or less done with the Clausius-Mozart equation, which is really important because it relates the microscopic and macroscopic quantities. And also we have seen that this equation is not valid for the polar materials like water or some ferroelectric materials. Okay, so the topic now that I'm gonna introduce, which is more theoretical rather than all the quantities or equations that we have introduced till now, it is called the polarization mechanisms. So few of the, let's say one of the polarization mechanism we already saw, but let me write it down, how many types of them are there. So first one is called electronic polarization. Okay. The second one is called the ionic or atomic, or sometimes it's also called vibrational polarization. So actually there are 5 types total. The third one is called dipolar or orientational. And the fourth one is called interfacial. Ouch. Interfacial polarization. And the last one, it's a spontaneous ferroelectric polarization. So all these polarization mechanisms, they depend on what kind of material you have, what kind of bonds they are having. So that's why, what are the properties of that material, whether they are ionic, covalent, or the bonds, or whether they are polar, or whether they have some spontaneous polarization in it. So all these characteristics of the material, that tells you whether you are going to have electric, ionic, or which one of these 5 polarization mechanism in the dielectric material. So I'll briefly discuss them one by one, not really rigorously, calculating or doing some derivation, but just to give you a brief idea how these mechanisms work. So first one is, let's say, electronic one. So this we already saw, the electronic polarization. So electronic polarization, and all the material has this electronic polarization. Why? Because all the material contain atom. Okay, so I can just write down All materials have it. Then it depends on what is the amount, what is the quantity, right? When we are comparing, let's say, because in some because let's say in some of the material, the electronic polarization is always there, but the ionic one would also be there. So then we have to see which one is more dominant over which one. So this decides whether it will be ionic or more electronic. So let's first, just because we have already seen this, so what happens in electronic polarization? So whenever you apply, it's just the separation of electronic charge. So we had a nucleus, the electron was surrounded by it, electron clouds. Once you apply an electric field, the nucleus remains as it is, but the electron cloud gets distorted. So let's say this is negative. So before the center of mass of both the electron as well as the nucleus, it coincides, but in the presence of electric field, it just gets separates out. So for example, we can denote this distance using the x. Okay, so this kind of polarization mechanism, it's called the electronic polarization. And what is the time scale actually? So the time scale in which the separation occurs, it's of the order of 10 to the power minus 14 seconds. Pretty quick, because it's atom also, right? So you can think of, we are not talking about in terms of seconds, it's 10 to the power minus 14 seconds. So which will be associated with a frequency of 10 to the power 14 hertz, the frequency. So this is, let's say, the time. And 10 to the power 14, so I can think of the electromagnetic wave. So whenever this field interacts with the dielectric material, so it causes the electronic polarization in the system. So let me just write down this field interacts with dielectric material and causes electronic polarization. Okay, so that's why, because of the frequency, it is also called the optical polarization. So I can just say electrical optical. All right, so this was electronic polarization. Actually, you can calculate a formula for this, but exactly by seeing how much charge has been displaced, then calculating the force using Coulomb law, then the dipole moment, and all the quantities that we have defined till now, the alpha, the polarizability. But I'm not going into the derivation. I just want you to know what are the basic mechanisms. So first one is the electronic polarization. The second one is the ionic one. The ionic, atomic, or vibrational polarization. Okay, so these kind of polarization mechanism. So the dielectric, which are having ionic or covalent bonding, they exhibit this kind of polarization. So let's start with an example such that I don't have to give a lot of theory, but you understand the basic physics. So any ionic crystal I can think of, the simplest one, let's say NaCl, the linear drive. So one is Na, NaCl. Let me draw 4 of them. And sorry, my circle are not exact circles. So let's say this is Na plus, the cation, and this is Cl minus, the anion. and I can also just, let me just label them 1, 2, 3, 4. Okay. The lattice constant is, let's say, the average value, because of course all the anion cation, they are oscillating around their equilibrium position, and that's why I'm saying the average separation between the anion and cation is A. This thing goes on. And the vibration of ions or the atoms, we know they are called phonons. Okay, that's the background. But now imagine this is our system. This is, let's say, the first picture. No, let me call it the picture A. Now what happens? Picture B. When we apply an electric field, E. So if electric field is in this direction, I can think of, let's say, plus side is here and minus side is there. All right. Okay. So what happens in the presence of external electric field? So the positive the cation that we call the Na plus, it gets attracted towards the negative end, and the Cl negative, the anion, it gets attracted towards the positive end of the electric field. So how this structure behaves? So let's say the cation 1 and 3, they move towards the right. So I can also do this 1, let me draw it like this, 1 and 3. Okay, so 1 and 3 will move towards the right. So this is, let's say, 1, and the position of 3 was somewhere here, but now it will go to this position. So this is 3 now. Okay, the position. And the position of 2 and 4, the anion, it will shift towards the left. So 2 will move this side, and let me draw it a bigger sphere. This is, let's say, 4, this is 2. So now you can see that this distance is smaller than A, right? So let's call it delta. The distance is smaller than A, and this distance, delta, is greater than A. Similarly, this one is smaller than A. So you see, now because of this, each individual ion, it changes, the distance between them changes. Okay, so because of that, the overall there is a generation of an electric polarization in the system. All right. So let me draw one more figure. If, let's say, our electric field is in the opposite direction, something like this. So then this side would be positive, this side would be negative. Then what will happen? The number 1 would move towards this side. Three will move this side. 2 will move towards this side, and 4 will move towards the right side. The chain goes up. So then the delta will be here greater than A, and this will be, the in between one would be less than A. So you can just try to do it yourself. Just remember one concept: the plus sign, the cation would get attracted towards the negative end of the electric field, and the anion would get attracted towards the positive side of the electric field. Okay, and you yourself can clearly depict what will be the position of the anions and cations in the system once you apply the electric field in whichever direction. Okay, so this is more or less what is called the ionic polarization. Okay, And also just another point, the anion would be in bigger size than the cation, right? Because anion's electron cloud would be more dispersed. It has extra electron, Cl negative, compared to the anions. And also, as I said, there will be electric polarization also. So that we didn't consider. I didn't tell you explicitly, but there will be, let's say, each of the, this is if I'm saying Cl, so there will be a nuclei, there will be an electron cloud outside, so there will be the, each of them will have their electronic part as well. So that's why the total would be, let's say, alpha E plus alpha I, okay, in the Clausius-Massotti equation that we wrote. But just to tell you the time scales, so the time scale of this these fluctuation is of the order of 10 to the power 13 seconds. Here, let's say time is of the order of 10 to the power minus 13 seconds, which is too much. So 10 to the power minus 13 seconds. So, and you remember in the electronic one, I told you it's of the order of 10 to the power minus 14. So here it takes a bit longer, 10 times more. Why? Because the anions or cations, they are heavier than the electrons, so they are sluggish. Okay, so that's why they move a bit slowly. So the frequency which will come out from this would be of the order of 10 to the power 13 hertz. Okay, so now we can clearly say that which one would be more. Of course, the alpha I would be more than the alpha electronic part. Okay, because this one takes longer time than the electronic part. Okay, so this is, let's say, the ionic polarizability. Then we can write down briefly discuss the third one, which is called the dipolar or orientational polarization. Okay, so what is dipolar or orientational polarization? So this appears where molecules known as polar molecules have a permanent dipole moment. Okay, so for example, water, H2O, right? And why they have a permanent dipole moment? Because of the proper orientation. It's such that the orientation of HO and the other HO, it doesn't cancels out. Okay, so you have an effective polarization, dipole moment in the system. So this leads to the something called dipolar polarization. So if I can just draw it down, for example, if we have, let's say we have a system where the water molecules, there are water molecules inside, and in the absence of electric field, so if I'll calculate the average polarization, P average, this will be 0. Okay, because the dipole moment of each individual water molecule will be in different directions, the average would be 0. But let's say if we apply an electric field, so what will happen? The P average, it will be some non-zero quantity, meaning, of course, depending upon the E, meaning if we have pretty large E's, so all of them would try to align along the electric field. But for a moderate one, let's say still there'll be something like this, but there will be an overall polarization in the direction of electric field. All right, so these kind of mechanism which appear inside a polar molecule. It's called the dipolar polarization. Okay, and you can also see that if, let's say, I increase temperature, even though we have electric field in the system, so what does temperature does? So temperature randomize your system. So your dipoles would be, it will favor the randomization. Well, an electric field wants to orient. So these two things, they are not compatible, temperature and electric field together. So in the presence of temperature, the effect gets suppressed. Okay, so the polarization decreases once you increase the temperature. And when I so you know that the measure of the polarization is via dielectric constant. So the dielectric constant in the, let's say, water vapor, or there are other example, which is nitrobenzene. So I can say nitrobenzene, and if I want you to write the chemical structure, it will be C6H5CO3. So the dielectric constant, if we increase the temperature, it decreases. It decreases with increasing temperature. Okay, so there are other materials also, hydrogen sulfide and so on, but I'm not going into that. So now the fourth mechanism, which is called the interfacial polarization. So as the name itself tells you, interface. So whenever, let's say, you have a grain boundary in the system, so there the charge actually adds up and you have a double layer kind of capacitor. So let me give you with the drawing. So for example, let's say here are our electrodes, okay, this one and this one, and these are the charges, if I can show inside. Okay, right now there is no electric field, so everything is kind of random, plus minus inside the dielectric material. So if we have mobile ions there, and then in the presence of electric field, meaning, let's say now this is plus, this is minus, okay, so our electric field is like this. So what happens? So generally, let's say here we say that the negative charges gets here, the positive ones inside the dielectric gets that side. But if you have, so this is, I can say, charge accumulation. So in the presence of grain boundaries, what happens? So let's say something like this, some boundaries, something like this are there. So we have negative this side and positive this side. Similarly, we'll have negative this side and positive this side. So these are grain boundaries or interface. Okay, so in the presence of these interfaces, we have kind of a double layer like, right, capacitor in the system. So this is what is called interfacial polarization. And most of the time, if you see the really high dielectric constant, meaning of the order of 30,000, 35,000, just to remind you, the dielectric constant of air is 1. Okay, so compared to air, if you see pretty high dielectric constant, so your first guess would be there has to be interfacial polarization, because these kind of processes are involved in the supercapacitors. Okay, and the example are some dielectric constant of calcium, copper, titanium oxide. It's a ceramic, CCTO we call it. Okay, so just to give you an example, let's say CCTO. So calcium, copper, titanium oxide. This O means. All right, so then we reach our last polarization mechanism, which is spontaneous or ferroelectric polarization. As the name itself tells you, spontaneous, so which means that there has to be a material which exhibits spontaneous reversible polarization. Okay, so this polarization typically, so what are the materials? Those are mostly the ferroelectric materials. So I can just say ferroelectric material which is defined as a system having a spontaneous polarization. Okay, and this polarization is very large in magnitude also compared to the electric or the ionic one. And the example of the ferroelectric material which has spontaneous polarization is, let's say, BaTiO3. Okay, so example BaTiO3. Okay, so here are the 5 mechanisms that we saw: electronic one, which all the materials have, then the ionic one, then the dipolar or the orientational one, then the interface one, and the last the spontaneous one or the ferroelectric polarization. So actually in the next lecture we'll see in detail what are these ferroelectric materials, because they are also really important class of materials. So we'll see ferroelectric and then ferroelectric materials in the next lecture.